Okay, so if we're interested in just positive correlation, then we will just do a dot max, right? So DF9C, which is the result of finding the correlation of this data frame, we can, first of all, the first thing that we do immediately is to dot replace 1 with 0. Remember what replace, what it does is to locate all the contents that has 1, right, and replace that with 0. And reason is it is always going to be the largest, right, across the diagonal. No other cell will have 1. And assuming that no other practical experimental measurements, field collection of data, will be perfectly correlated. That means having a correlation value of 1 with another field measurement. It can be very high, like 0.95. That's like amazingly high for data gathered from the field. And assuming that it will never be 1 exactly, then we can just replace the value 1 here across the diagonal, because that is always going to be theoretically exactly 1. So we just replace 1, right? Even though by right we should be like scanning for the diagonals and then replace those with zeros. But I think it's safe for most general purposes with just replacing value 1, assuming that 1 doesn't occur in the off diagonal cells. So that's quite a convenient and quick and easy way to do it, and most of the time should be correct. Dot replace 1 with 0. Okay, so once the diagonal ones are all removed, then the max of the resultant data frame will be pretty interesting. So we say, what is the resulting dot max? And that would give us 0.34, right? So we ask for the entire data frame DF9C, look at the entire data frame with the diagonal being zeroed out, which cell matches the max? And of course, this turns all the cells equal to 0.34 to true and all others to false. So in my case here, it will be the top right and the bottom left. These two cells will be equal to true and the rest will be false. So I've managed to quickly get a mask, right? So df9c equal to df9c.max. This will give me a mask to select from the base data of df9c, right? Whatever is the equal to the maximum. Using that, I'll be able to therefore obtain, a sort of a true false mask. No, here I will get basically a data frame, and then I sum up, right? So from df9c selecting df9c equal here, I will get a data frame of true false, and then I will get NA, and then 0.34, NA, and 0.34, and so on. So I will then be able to sum up, okay, do a dot sum, and that, remember, dot sum gives us a column sum, and that number, if it's greater than 0, will be set to true, and otherwise not true. Right? So when we have the truths being added up, we will get, of course, B here will have a 1, C here will have a 0, because it's false, right? 0, 0, 0. And D here will have a true 0, a false, so it will be 1. So 1, 0, 1. 1, 0, 1 will be then, remember this dot sum gives us a series. So it's going to be greater than 0 will be true, false, true. So true, false, true. And then we plunk it into the selector of the dm9c.index, which is this BCD here. Okay. So therefore we have, and because the index is the same as column, we can then say true, false, true. And maybe we can just put it as df9c.columns just as well, no problem. And then we will have we will be able to select B and D coming out of it. And then we force list it, we'll get this list of B and D. So after this calculation, our cols, COLS, will contain a list of any column that contains the largest correlation value. Now, assuming the largest is unique, as in the half triangular table here. If it is unique, for example, we don't see B and C being 0.34 also. All right, so unique in the sense of the upper triangular matrix, then we definitely will see two columns being listed out. If that's the case, that's good, because now we are seeing this interesting report telling us that B and D, maybe in our database, it is actually stored as income and years of education, right? So if that's the case, then it will immediately highlight to us, oh, maybe we should look at these two sources of data to examine further. So that's on basic statistics. And .core, you may or may not like it, but it's really very useful, even perceptive first step, that you hardly need to do any calculations, and so easy to call it out, so easy to scan for interesting columns to look at, right? So it is kind of a must. You should do it almost immediately, right? In addition to performing all the usual descriptive statistics like finding the average standard deviation. But .core is like you know, very cheap in terms of preparation and execution time, a very cheap way to obtain the results. And maybe after looking a bit further, we decide BND, no, not really. It's just an anomaly that .core identifies them. That's fine, right? So no harm done. So, but then what if the .core actually finds out something that we haven't been paying attention to? For example, if you're doing e-commerce and there are a lot of data being collected in the web-based transactions and payments and time delay and time duration to consider and time between clicking, wanting this item and checking out and all that stuff. So a lot of data being collected, and who knows, out of these, maybe the positioning of the checkout button on the screen is actually very decisive in terms of whether this item will enjoy higher chance of being purchased or not, right? So some of these things are really, I won't say unimaginable, but not so obvious that we will not spend time to really investigate unless we are told, right, by such a quick scanning mechanism to highlight to us that, hey, you know, I think there's something interesting there. Let's investigate further. So this .core, I really put it in the center here uh, to highlight the important um, role it plays. Very importantly, because you don't need much to set it up. When you import pandas, it's already there. So have a run at .core and use this quick expression to grab the column names of you know, high positive correlations. And of course, if you need um, high negative correlations, just put a dot min. And of course, if you need anything that is interesting, whether it's positive correlation, negative correlation, then just do an absolute value. Do a dot ABS of DF9C equals to the maximum of the absolute values. So quite easily computed, you know, so definitely have a run at it. The rest will be that like dot median, find the median, all right, find the median. And what is that? That's not across everything, but across the columns. Okay, so dot median, dot standard deviation, again, even if your whole data frame is full of numbers, no strings, dot standard deviation also calculates based on column kind of data. So you will have, if you have 3 columns, you will have 3 standard deviations like this. And then you have maximum, minimum. Those are important. For example, in identifying programmatically which is the interesting column, you know, having high correlation and all that. So we did use the dot max here. Okay, this dot max is yeah, basically the the uh the same function that we have shown here. Okay. All right.